All right, starting off. Let's go here for Luke. Yes. Yeah. So today we're going to reintroduce these concepts of torque and talk a little bit about what torque was and what things affected, et cetera, et cetera, et cetera. Then we'll see you tomorrow. Friday, we'll probably finish up some torque stuff and then talk about rotational equilibrium. Rotational equilibrium will probably take us through here-ish, and then we're probably looking at WHS/test/quest somewhere like here. I know, there's been a lot of quests lately. That would be the last one. And then next Friday, and there it is, people. Well, Luke. Yes, ma'am. Probably partner, but kind of like the last one that we just did. So. But then, seniors, you guys get Wednesday if you have to take the exam. First block on Wednesday. So if you don't take the exam, then sleep in. But anyway, so that's what we're looking at there. As far as there's not much left. I think we're all aware of that. So there we go. All right. Last Tuesday, we introduced this concept of torque. And we talked about the idea that a lot of times, well, an object will be both moving through space, or flying through the air, or moving in a straight line, whatever it is, but also could be rotating while it's moving through space. And we have this little time-lapse picture here that represents a hammer being thrown. Okay? I don't suggest that you throw a hammer through the air, but here you can see down here at the bottom that there's the head of the hammer, there's the handle of the hammer, and it gets thrown, so it's twisting as it falls, as it goes through space. If we look at the red line, I think we mentioned the other day that this red line is going through a parabolic path, just like any projectile would if we threw it through the air. Okay? But it's also rotating as it's going in that projectile path. And we introduced this concept of torque. Torque is what causes changes in rotational motion, or angular acceleration. It causes things to speed up how fast they're spinning, or slow down how fast they're spinning. We looked at it sort of as the rotational equivalent of force, right? There we go. Force causes changes in translational motion. It causes things to speed up or slow down or change directions. But torque causes changes in rotational motion. It causes things to spin faster, spin slower, not spin at all. Well, not spin at all. We'll talk about that more on Friday. But then we said that torque depends on two things. It depends on the force applied to the object and the distance from the center. And I think the other day we introduced this formula. Torque is equal to F times D times sine of theta, where this lowercase Greek letter tau, we use that to represent torque. Torque depends on the force. It depends on the distance we are from the center. But the fact that we're including some angle and some side of the triangle means we're probably going to have to deal something with lost my train of thought. Components. So that's something to deal with components. Okay. So looking at this picture, okay, first quick survey. Did any of that sound familiar? Yeah. Okay. For real? Not just saying. Okay. Good. So as far as this formula for torque goes, this is lowercase tau. It's just written in different fonts. So here, there's our force, right? That's the force we're actually applying to that object. And then this is our D, which we refer to as the lever arm. That's the distance we are away from the center of the rotation. And then this angle theta here is going to be the angle between the force and the lever arm. And that's important because I think we talked about that not all forces are going to produce torque. Only forces or components of forces that are perpendicular to the lever arm produce torque. And I think the other day we did the demonstration with the wheel. Yes? I think you did it, right? Okay. So we talked about applying the forces to different places, right? That when you pushed at point A, which is this tape mark, the one farther away from the middle, what did you find about how turning the wheel? It's easier than when you apply the force at B, which is closer to the center. But the last thing I did, you remember the last thing I had you do?
So I pushed like...
Yeah, like push towards the middle, right? And what happens? Nothing happens rotationally, right? Because, that will stay, because forces parallel to the lever arm, or forces that pass through the center of rotation, result in no torque. They may result in moving that object translationally or through space, but they won't cause it to spin. Is that good? These are available online. All right, we'll get there. Okay, so if we apply this force, like we pushed, if somebody's hand came in and pushed in this direction on like the end of the wrench, right, nothing's going to happen, at least not rotationally. Nothing is going to spin. There's going to be no change in the rotational motion. If we go back to the whole sine theta thing, right, that was a glitch. Was that request? Or was that just reflection? Okay.
Request to yourself.
What's that? All right. So here, if we look at this force and how it's acting sort of on the wrench, if we pull, a lot of times when you pull the wrench, you don't do this, but there's components here. This component, I guess if you want to like, in the,
The wrench doesn't move by itself.
True.
Sorry, I wanted to know how.
No, that's fine. No, it's not. But if we look here, this force has some components, right? This component here, if we're looking at the picture of the quote-unquote horizontal component, that's the one that's going to cause the torque. That's the one that's going to cause us to spin. This force here, if we look, the center of rotation is this nut, right? If a force passes through the nuts, right, does anything happen, at least rotationally? Nothing happens rotationally. And there we go. We just talked about those two things. So, if we had this wrench, right, what's the best way to turn it? Which force is going to cause the biggest torque? The end one, this one down here, F of B, right? If you have to turn a nut, if you have to turn a screw, right, or let's say not a screw, but if you use your fingers, right, hard or easy to make the nut turn? Harder than if you use like a wrench, right? Because if we look, we said that force depends on basically two things. It depends, or sorry, torque depends on two things. Ooh, that's not torque, that's J. Don't want J. Come on, here we go. Torque depends on two things. Torque depends on force, but it also depends on distance, right? If we're talking about using your fingers, the distance that we're talking about is only this distance from here to here, right? The distance from the center of the nut to the edge of the nut, because that's how far away you are from the center. But when we use the wrench, right, now we can get this far away from the center. And that increases P in this formula, and that ends up with more torque. We get more rotation. Good.
So when you said with that wheel thing and there's a component, the force, it's just the perpendicular one?
The force that causes torque is only the perpendicular one.
But
Okay?
value 1 is the, like, guys.
Right. So like here, yeah, like when we introduced the actual formula loop, we said this, and then sine theta, right? Okay. The sine theta part takes care of the perpendicular component of that force. So when we include it in that formula, that automatically gives us the perpendicular component. So you don't have to break it up into components and then do it. Including sine theta in that formula automatically does it for you. Okay. Good there? Questions? Come on. There you go. Oh. So, here, multiple forces, right? Which force causes the biggest torque? It's got three forces and a couple different angles, right? There's one force out of these three that we can eliminate right away. What's O stand for in this picture? No, not theta. Theta's an angle. Sorry. This is the rotation point. This is the spot that we're spinning around. Okay? So out of these three forces, we can eliminate one of them right away, right? The one on the left. This one is not going to cause the biggest torque. Why not? Not necessarily close to the rotation. It actually passes through the center of rotation, right? So will it cause any torque at all? No. Okay. Then we have to take a look, right? Here, the lever arm of this 10 Newton force is much longer, twice as long, right? But now we have to look at values as far as what we get, okay? Remember, we have to look at only the perpendicular component is the one that's going to cause the torque, right? Go ahead, Alicia.
I'm confused.
Okay.
What are you turning?
So it's just some bar. I don't know why. Like here, this is the spot that we're spinning around right here. Okay, and we're like, causing it to spin like that. Does that make sense? Okay. So, Lauren, did you start punching these things in your calculator?
Yeah.
Okay. What did you find out?
The middle one?
Middle one. I don't know the answer off the top of my head. So what did you do to find? What did you do to find out which one caused the biggest torque?
Well, first I did distance that it is from.
Okay, so 2, right?
Times 25.
Times 25 times
And then times sine of 31.
sine of 31. That'll work, and that'll get you, because the sine of 31 gets you this component right here, right? Okay, so what'd you get for that?
25.75.
Okay, so 25.75, and as far as unit goes, that would be newtons times meters. That's our unit for torque. Okay.
The other one's the same thing, but it's 4 times 10 times sine of 23.
Okay. So then
You get
4 times 10 times sine of 23. Sine of 23 will get you that component, right? And what'd you get?
15.63.
15.63. Once again, newton times meters. So this force causes the biggest torque, even though it's closer to the middle. Jump ahead.
What's the difference between torque and lever?
Basically nothing. Then it's just a different way of leverage. I guess is kind of more of a sort of everyday term that we use to describe torque. Okay.
Oh, it's pretty much.
Yeah, pretty much the same thing. All right, good there. All right. That wasn't so bad, now was it? Not that we're done yet, but let's check. 21 minutes. All right, 21 minutes. Stay strong, everybody. Stay strong. What? People are starting to drop off here. So. Tom's here, though. Tom's gonna put in a solid 21:06 today. So. All right. Let's take a look